Welcome to lecture 41. So, this is the first lecture of week 9, and in this week 9 we will talk about simplex method for solution of linear programming problems. We have talked about graphical solution method for linear programming problem, and we have seen that the feasible region is the polygon. So, one way to solve a linear programming problem is to evaluate each corner of this polygon, because we know that the optimal solution will lie at one or more of these corner points. So, this may be convenient for a very small size problem, but for a large scale problem you may have very large number of corner points, and evaluating each corner point is not an easy option. So, we need more robust method for solution of linear programming problem, and simplex method is one of such efficient method. So, today we will start our discussion on simplex method for solution of linear programming problems. So, we have seen in case of graphical solution that optimal solution will always be at one of the corner points. So, an enumeration approach will be to substitute the coordinates of each corner point into the objective function and determine which corner point is optimal. But this will be an inefficient approach for large scale problems. So, simplex method is an iterative procedure. It begins at a vertex of the feasible region. Each iteration brings us to another vertex of the feasible region with an improved value of the objective function. The iteration ends when the optimal solution is reached. The algorithm tries to find the optimal solution by visiting minimum number of corner points. So, if you look at the figure, we start from this vertex, and the way we visit each corner points is shown by the arrow mark, and we reach the optimal solution by visiting a small number of corner points of the total number of corner points. So, to start our discussion on simplex method, let us first revise what we learned in our previous lectures about canonical form. So, what you see on the screen is the general formulation of a linear programming problem. You have the objective function, which is a linear function of n variables. You have m number of equality constants, and you have non-negativity constants on the decision variable and the constants on the right hand sides of the constants. In general, you will have fewer number of constants compared to number of decision variables, and this leads to infinite number of feasible solutions. Hence, selection of best feasible solution which maximizes the objective function may not be an easy problem. To generate the solutions, we first use m variables to reduce the system to a canonical or row echelon form by Gauss-Jordan elimination. Then we can have a working solution by converting or putting the values of the remaining m plus 1 to n variables as 0. So, before that we have to convert the set of equations into its canonical form by performing n pivotal operations. A pivot operation is sequence of elementary row operations that reduce the coefficients of a specified variable to unity in one of the equation and 0 elsewhere. So, if you look at the first equation, the coefficient of x 1 is 1 and the coefficient of x 2, x 3 up to x m are all 0. So, we have considered x 1 to x m as pivotal variables and we have the remaining variables x m plus 1 to x n. So, in the canonical form you look at the x 1 to x m part of the set of linear equations. In the first equation only coefficient of x 1 is 1, in the second equation only the coefficient of x 2 is 1 and in the mth equation only the coefficient of x m is 1. So, this is known as canonical form. Please note that these coefficients as well as the right hand side coefficients or constants all have changed from their original values due to series of elementary row operations for conversion of the system to its canonical form. So, in the canonical form x 1 to x m are termed as basic variables or dependent variables and x m plus 1 to x n are called non-basic variables or independent variables or non-pivotal variables. Now, if you look at this canonical form, if I put the values of x m plus 1 to x n variables which are non-basic or independent variables as 0, I can readily solve the equations and the solutions will be x 1 equal to b 1 bar, x 2 equal to b 2 bar, x r equal to b r bar, x m equal to b m bar and so on and so forth. So, the solution obtained from a canonical form by setting the non-basic variables or independent variables to 0 is called a basic solution. So, the basic solution is obtained by setting the values of the non-basic variables to 0. So, in general I can write x I equal to b I bar for I equal to 1 to m which are basic variables and x I equal to 0 for I equal to m plus 1 to n which are non-basic variables. So, this solution will be known as basic solution. Variables x 1, x 2 up to x m are also known as basic variables. Variables x m plus 1 to x n are also known as non-basic variables. A basic feasible solution is a basic solution in which the values of basic or dependent variables are non-negative. That means, b I bar is greater or equal to 0. So, a basic feasible solution is a basic solution in which the values of the basic or dependent variables are non-negative. In other words, basic feasible solutions are those basic solutions for which b I bar is greater or equal to 0. How many number of basic feasible solutions are possible? Let us consider that we have m linearly independent equations in n variables. Any set of m variables can be selected as basic variables out of the possible n variables to obtain a canonical system and a basic solution. In the previous example shown, we have considered first m variables as basic variables, but if you can consider any set of m variables as basic variables out of the possible n variables. Thus, the maximum number of basic solutions is NCM, which is factorial n divided by factorial m into factorial n minus m. Every basic feasible solution is also a basic solution, hence the maximum number of basic feasible solution is also NCM, which is factorial n divided by factorial m into factorial n minus m. Note that by evaluating each basic feasible solution, one can find the optimal solution for the linear programming problem. The simplex method is an efficient iterative procedure that finds the optimal solution by evaluating a small number of total basic feasible solutions. So, here are the general steps for the simplex method. First, we have to express the linear programming problem in standard form. We know what is standard form. By standard form, all the constraints will be equality type, decision variables, and the right hand side vector will be non-negative. After expressing the linear programming problem in standard form, we start with an initial basic feasible solution in canonical form. Once we have a starting basic feasible solution, we would like to improve the solution by finding another basic feasible solution with a better objective function value. So, if I am maximizing a problem, I would like to find another basic feasible solution with an objective function value which is higher than the current basic feasible solution. At this step, the simplex method eliminates from consideration all those basic feasible solutions which are inferior compared to the present basic feasible solution. We continue to find improved basic feasible solution when a particular basic feasible solution is found and cannot be improved by finding new basic feasible solution, the optimality is reached. So, this is in general the steps of a simplex method. So, the key steps are: you start with an initial basic feasible solution and then you have to find at each iteration an improved basic feasible solution than the current basic feasible solution. When we cannot do that, optimality is reached and we stop. So, the question that we ask now is how to obtain the improved basic feasible solution. So, let us consider we have an initial basic feasible solution in canonical form as shown. Basic variables are xi equal to bi bar and bi bar are all greater or equal to 0, so that their basic solutions are feasible. So, I equal to 1 to m basic variables and non-basic variables xi equal to 0 for j equal to m plus 1 to n. The set of basic variables is called a basis and we represent this basis vector by x b. Let the objective function coefficients of the basic variables be denoted as c b. So, x b is basis vector. So, its components are the m basic variables and objective function coefficients of basic variables are denoted by CB. So, CB is the vector with components objective function coefficients for basic variables C1, C2 up to Cm. Since the non-basic variables are 0, the value of the objective function z corresponding to the initial basic feasible solution can be obtained as C1 B1 bar plus C2 B2 bar up to Cm Bm bar, that means Cb into Xb, vector product of Cb and Xb. Now, given the initial basic feasible solution, the simplex method first examines whether the present basic feasible solution is optimal or not. If it is not optimal, the simplex method finds an adjacent basic feasible solution with better or at least equal value of the objective function. So, when we start with an initial basic feasible solution, the simplex method will first examine whether the present basic feasible solution is optimal or not. If the present basic feasible solution is optimal, we stop our algorithm. If the present basic feasible solution is not optimal, we have to find an adjacent basic feasible solution with better or at least equal value of the objective function. So, what is adjacent basic feasible solution? An adjacent basic feasible solution differs from the present basic solution in exactly one basic variable. So, a basic variables will be removed from the basis and a non-basic variable will enter the basis, so that the new adjacent basic solution differs from the current basic solution in exactly one basic variable. Note that you have m basic variables. So, your basis contains m basic variables. The adjacent basic solution or the adjacent basic feasible solution will be another basis vector with only one component different. So, in order to obtain an adjacent basic feasible solution, the simplex method makes one of the basic variables a non-basic variable and converts a non-basic variable to a basic variable in its place. So, the question we now ask is how to select appropriate basic and non-basic variables that gives maximum improvement to the objective function. So, you understand that adjacent basic feasible solution differs from the present basic solution in exactly one basic variable. So, one non-basic variable will be converted to a basic variable and one basic variable will be converted to a non-basic variable. So, the question is how to select appropriate basic and non-basic variables so that their exchange gives maximum improvement to the objective function. That means, for maximization problem, we should get the maximum increase in the value of the objective function after the exchange of basic and non-basic variables. A basic feasible solution has non-negative value. So, basic feasible solution is always greater or equal to 0. The non-basic variables are always 0. Thus, when you convert a non-basic variable to a basic variable, we increase its value from 0 to some positive quantity. Note that all decision variables are constrained to be greater or equal to 0, but a basic feasible solution can be values which are greater than 0. Non-basic variables are always 0. So, when we convert a non-basic variable to a basic variable, we increase its value from 0 to some positive quantity. We have to choose that non-basic variable that causes maximum improvement in the objective function. To determine this, we can increase the value of non-basic variable by 1 unit, say 0 to 1, and check the change in the objective function value. Note that the values of other non-basic variables will remain 0. So, to determine which non-basic variable will be converted to a basic variable, what we can do is we can increase the value of a non-basic variable by 1 unit, say from 0 to 1, and check the effect in the objective function value. So, for a maximization problem, we would expect that this will increase the value of the objective function. So, let us see how we can do it. Let us select the non-basic variable xs and increase its value from 0 to 1. Values of all other non-basic variables remain 0. So, let us look at again the canonical form. So, first m variables are basic variables, and then m plus 1 to n are non-basic variables. What we are saying now is, let us increase the value of the non-basic variable xs from 0 to 1. So, if I do that, the canonical form will be rewritten as shown. It was x1 equal to b1 bar, x2 equal to b2 bar, etc. Now, it will be x1 plus a1s bar xs equal to b1 bar, x2 plus a2s bar xs equal to b2 bar, and so on and so forth. So, when we increase xs from 0 to 1, we get a new solution. Initial solution was xi equal to bi bar, but now you see the solution is x1 equal to b1 bar minus a1s bar xs, x2 equal to b2 bar minus a2s bar xs, etc. So, the solution can be written as xi equal to bi bar minus ais bar for I equal to 1 to m, all basic variables, xs value of xs equal to 1 and xj equal to 0 for j equal to m plus 1 to n, and j is not equal to s. So, since the values of the basic variables have changed, so the value of the objective function has also changed. So, the new value of the objective function can be obtained as shown. Note that the value of the objective functions are nothing but the the basic variable multiplied by its coefficient, objective function coefficient, the cost coefficients. So, for all I equal to 1 to m. So, basically these are Ci into xi. Note that this is nothing but Ci into xi for all I equal to 1 to m, and then this is xs into cs, where cs is the cost coefficient of xs, but xs equal to 1. So, Cs into xs is same as Cs. So, we now get the new value of the objective function. So, what is the net change in the value of the objective function per unit change in xs? To find this out, we have to get the difference between the value of the new objective function and the value of the old objective function. So, this net change in value of objective function z per unit change in xs is known as relative profit of non-basic variable xs. So, it is denoted as Cs bar. So, Cs bar is obtained as the new objective function value minus old objective function value, and this is obtained as Cs minus sigma I equal to 1 to m Ci Ais bar. This is known as inner product rule. So, if the relative profit of non-basic variables Cs bar is greater than 0, then the objective function z can be improved by making xs a basic variable. For a maximization problem, we should therefore choose that non-basic variable which has maximum positive relative profit value. Note, for basic variables, this relative profit Cj bar equal to 0. So, this answers the question which non-basic variable will enter the basis. So, we will find out the relative profit of the non-basic variables, and if the relative profit is greater than 0, we understand that the objective function can be improved by making xs a basic variable. For a maximization problem, we should choose that non-basic variable which has maximum positive relative profit value, so that will cause the maximum improvement in the objective function value when we convert that particular non-basic variable as basic variable. The relative profit coefficient of a non-basic variable xj is given by Cj bar equal to Cj minus Cb into Pj bar. Here Cb corresponds to the profit coefficients of the basic variables and Pj bar corresponds to the jth column in the canonical system of the basis under consideration. So, you understand the inner product rule which says for a maximization problem we should choose that non-basic variable which has maximum relative profit. So, now this also leads to the condition of optimality. In a maximization problem, a basic feasible solution is optimal if the relative profits of all the non-basic variables are negative or 0. That means, Cj bar is less or equal to 0 for all non-basic variables. When the relative profits of all non-basic variables are less or equal to 0, then every adjacent basic feasible solution has an objective function value lower than the present solution. Thus, the current solution is the local maximum. Since a linear programming problem is a convex programming problem, the local maximum becomes global maximum. So, when for a maximization problem, we have the relative profits for all non-basic variables are negative or 0, that means there is no adjacent basic feasible solution which has an objective function value which is better than the current one. So, the current solution is the local maximum, and since linear programming problem is a convex programming problem, this local maximum is also global maximum. So, you understand now which non-basic variable enters basis, but then which basic variable leaves basis, that means which basic variable becomes non-basic. Let us consider that Cs equal to max Cj bar which is greater than 0 and the non-basic variable xs has been chosen to enter as basic variable. Then the value of the basic variables change as xi equal to bi minus ais xs. So, look at this expression now. Xi equal to bi bar minus ais bar xs. So, this equation tells us that if ais bar is less than 0, then xi increases as xs is increased. If ais bar equal to 0, then xi does not change as xs is increased. If ais bar is greater than 0, then xi decreases as xs is increased and may turn negative. That means, it may become infeasible. So, how much increment should I make to xs? So, thus the maximum increase in xs is given by a rule known as minimum ratio rule. So, maximum xs is minimum of all ratios which are bi bar, ais bar. Note that xi equal to bi bar minus ais bar xs. So, if I put xs equal to bi bar divided by ais bar, xi will be equal to 0. Beyond that, if I increase, it will become infeasible. So, we have to find the ratio of bi bar divided by ais bar, and then minimum of that will give me the maximum increment in xs. If this happens at I equal to r, xs is increased to br bar by ars bar. Here r means the rth row. So, thus xs is increased to br bar divided by ars bar and the basic variable xr becomes 0 and is replaced by xs. So, to find which basic variable will leave basis, you have to find out bi bar divided by ais bar, and then you take the minimum of this. So, look at the row at which this minimum happens, and that will tell us which basic variable will leave basis. This will be more clear when you solve a problem. So, there are two main rules, one was inner product rule and another is minimum ratio rule. Inner product rule says that non-basic variable which has maximum positive relative profit value becomes basic variable, and minimum ratio rule says that basic variable which has minimum ratio becomes non-basic variable. So, after this exchange of basic and non-basic variables, the simplex method checks again if the current basic feasible solution is optimal by calculating the relative profit coefficients for all non-basic variables, and the cycle is repeated until optimality conditions are reached. With this, we stop here, and in the next lecture, we will take a problem and solve usually linear programming problem to understand the ideas better.